Welcome everyone to this fifth lecture of states of matter. So in the previous classes, we have seen about the various states of matter, which are liquid, solid, and gases. And then we have also seen about the two laws that are the Charles law and Boyle's law, and we have also seen the relationship between temperature and volume and pressure and volume, right? And we have also plotted some graph, and we have also read how to plot, how to understand the nature of the graph, right? So in this lecture, also we are going to study about some more laws. Like for example, we are going to study about Gay-Lussac's law, Dalton's law, Avogadro's law, and finally, we'll club all this together, giving rise to the ideal gas equation, and we'll also study about the kinetic theory of gas, right? As per time, okay. So states of matter. The first topic which we are going to study is Gay-Lussac's law, which is also pressure-temperature relationship. So the relationship between pressure and temperature was given by Joseph Gay-Lussac and is known as Lussac's law. Right? It states that at constant volume, pressure of a fixed amount of gas varies directly with temperature. So this one given this was given by Joseph Lussac, right? And this law states that at constant volume, pressure of a fixed amount of gas varies directly with temperature. Mathematically, this means mathematically it may be expressed as pressure is directly proportional to temperature, which means pressure equals to when we remove the proportionality, when we remove the inequality or proportionality, we include a constant which is kT, right? What does that mean? This means P by T is constant, right? This means P2 by T2 is going to be equal to P1 by T1, right? This relationship can be derived from Boyle's law and Charles law, right? So what is Boyle's law? Boyle's law is pressure inversely proportional to volume, and Charles law is volume is directly proportional to temperature, right? So the nature of the curve, if we plot, it's going to be 0. Okay. So we are going to get a straight line when we plot pressure versus temperature, right? So this is pressure, this is temperature, and the law which we are using, pressure is directly proportional to temperature, implies P is equals to KT, which is Y is equals to mx plus C, where C is equals to 0. And M is nothing but constant, and X is temperature, right? So it's going to be a straight line passing through the origin, right? Let's say these are all isochores, right? Isochores. The isochores means constant pressure graph. So let's say the constant volume graph. So this is, let's say, V1, this is V2, this is V3, and this is V4, right? So what we have is V1 less than, should I write it here? V1 going to be less than V2, which is going to be less than V3, which is going to be less than V4. That means as we go down, volume is increasing. The curve shows the pressure temperature behavior at fixed volume, right? And it's called as isochores. So this plot is called as iso, means constant volume graph or plot. So the next is physical significance. Physical significance, Gay-Lussac's. So pressure in a well-inflated tires of an automobile is almost constant. But on a hot summer day, this increases considerably and tire may burst if pressure is not adjusted properly, right? Similarly, during winters, on a cold morning, we find that pressure in the tire of a vehicle decreases considerably, right? Right? So pressure in a tire of a automobile, as pressure is, as per Gay-Lussac law, pressure is directly proportional to temperature. In summer, what we have, pressure will be higher in summer. Pressure exerted by a fixed amount of gas is higher than that in winter, because temperature in summer is going to be temperature in winter, and hence pressure in summer is going to be pressure in winter. Hence we are advised to keep less amount of gas during summer and more amount of gas during winter in our tire, right? So let us solve an example. So first question, a chamber of constant volume contains hydrogen gas, right? When the chamber is immersed, the chamber is in a bath of melting ice, which is at 0 degrees centigrade, right? The pressure of the gas is 1.07 into 10 raised to power 2 kilopascal. Now we are asked what pressure will be indicated when the chamber is brought to 100 degrees centigrade. So let us try to solve this question. What we are given is, we are given T1 is nothing but 0 degree centigrade. This implies T1 is 273 plus 0, which implies T1 is 273 Kelvin. Right? T1 we are given as 1.07 10 raised to power 2 kilopascal, which implies pressure 1 is going to be 107 Pascal, right? Kilopascal, sorry, 107 kilopascal. Plus we are giving T2 as T2 we have been given as 100 degree centigrade. This implies T2 is 273 plus 100, which implies T2 is going to be 373 Kelvin. And what we are asked to find is T2 is equals to constant, and we are also given as volume is constant. Right? Hence, we can use the Gay-Lussac law, right? Since volume remains constant, volume remains constant, we can use Lussac's law, which is pressure is directly proportional to temperature, which implies T2 by T2 is nothing but T1 by T1, implying T2 is going to be T1 by T1 multiplied by T2, right? Implies P2 is going to be P1. So what we are given, P1 as 107 kilopascal. Temperature 1 has been given as 273 Kelvin. T2 has been given as 373 Kelvin. Implies P2 is going to be 1.462 into 10 raised to power 2 kilopascal. So this is the final answer. Okay. So the next law which we are going to study is Avogadro's law. Avogadro law. This is also called as volume amount relationship. Volume amount relationship. So this law was given by Avogadro 1811. In 1811 he put forward the relationship between volume of gas with the number of molecules at constant temperature and pressure, and this now has been accepted as the law and is known as Avogadro's law. So this law states that at a given temperature and pressure, the volume of a gas is directly proportional to the amount of gas. So mathematically we can write that volume is directly proportional to the number of moles at constant pressure and temperature constant, right? Which means volume is equals to K times N, right? Where N is the number of moles, right? So the number of molecules in 1 mole of gas has been determined to be 6.022 into 10 raised to power 23, and N is known as Avogadro's constant, right? So the number of molecules in 1 mole of gas has been determined as 6.022 into 10 raised to power 23. So this is very important. 10 raised to power 23, and is known as Avogadro constant. Avogadro generalized the above observation by the following statement, right? And the statement which he gave is all gases containing equal amount of substance occupy the same volume at the same temperature and pressure. This means that 1 mole of a gas at standard temperature and pressure will have the same volume, right? So what does this mean? This means that 1 mole of gas at standard temperature and pressure will have same volume. And this is known as molar volume and denoted by Vm, right? And it has been found that 1 mole of any gas at NTP, that is 0 degrees Celsius, and 1 bar pressure occupies 22.71 into 10 raised to power minus 3 meter cube, or 22.71 liter, right? It is further shown that this molar volume at the same temperature and pressure has the same volume, right? and number of moles going to be mass of gas, the mass of a substance, let's say in kg, divided by the molar volume, molar mass, sorry, which is denoted as m by m. So the next law which we are going to study is combined gas law or ideal gas law, right? Combined gas law or ideal gas law. It is nothing but a combination of all the laws which we have studied, right? So Boyle's charge gives the separately variation of volume of a gas with pressure and temperature respectively. By combining these two laws, we get an equation which gives the simultaneous effect of changes of pressure and temperature on the volume of the gas. And this is known as combined gas law or gas equation, right? So let us consider unknown quantity of gas, at pressure P1, temperature T1, and having a volume of V1, right? Suppose that it is to be converted to another state having pressure, volume of V2, and temperature T2, right? So the first step is going to be, let us change the pressure of a gas from P1 to P2 at constant temperature, right? At constant temperature T1, the volume will change from V1 to V2, right? Since the temperature remains constant, the temperature remains constant, hence applying Boyle's law, which gives us P1 V1 is P2 into V2, where V2 is going to be P1 V1 by P2, right? Let us term this as equation 1, right? And step 2, what is going to happen? Let the temperature of gas be changed from T1 to T2. Okay. However, here we are going to say keep temperature as constant at constant temperature, constant pressure, sorry, at constant pressure P2, so that the volume will change from Vx to V2, right? Vx to V2. This is going to be the Vx, the intermediate volume, right? Thus, according to Charles law, what we have, Vx by T1 is going to be V2 by T2, which implies V2 is going to be Vx T2 by T1. From 1 and 2, what we get is, so this is equation 1. This is, so we are what we are doing, we are just substituting the value of Vx from here into this, right? Then what we get is V2 is going to be P1 V1 by P2 multiplied by T2 by T1, implies V2 is going to be P1 V1 by P2 into T2 by T1, right? Which implies, so we are going to collect the terms of one on other side. So we are going to remove, take this pressure from here to here. Similarly, this temperature from here to here, right? So what we get is, we get P2 V2 by T2 is going to be equal to P1 V1 by T1. In other words, what we can say, PV by T is going to remain constant. PV by T is going to remain constant, right? So in a diagrammatic fashion, we can the process which we have followed, we can show it as, this is P1 V1 T1, which was the initial state, right? Initial state. Now we want to go from here, this initial state to a final state, this final initial state to a final state of P2 P2 V2 and T2, final state. So in order to achieve this, what we do is we take a detour like this, which is like P2 Vx into T1, and then from here we going to step 1, which is constant temperature. This is step 2, which is constant pressure. And so this expression which we have just derived, PV by T equal to constant, is what is called as an ideal gas law, right? So let us understand the alternative derivation also. Alternative derivation for the gas equation. So according to Boyle's law, what we have? According to Boyle's law, we have volume is inversely proportional to temperature at constant T and N, right? Let us assume this expression 1. According to Charles' law, we have volume directly proportional to temperature at constant P and N. According to Avogadro's law, volume directly proportional to N, which is at constant P and T, right? So combining all this expression, combining equation 1, 2 and 3, what we have is volume is proportional to N T by P, which implies volume is proportional to, volume is equal to some constant K multiplied by NT by P, right? Implying P into V is going to be NT, and the right, it's going to be proportional to NT, right? So the proportionality constant, the value of K which we get is called as RT, right? So hence what we get is PV is equals to KNT. So this K proportionality constant is called as R, which is universal gas constant. Right? Hence we say P into V is going to be N R2. Okay, and this expression is called as an ideal gas expression, right? Or ideal gas law, right? And the value of R, right, is going to be, so there are many values of R which we have. Thus R represents, right? So let us understand the nature of this R. Nature of universal gas constant, which is R. Okay, so we know that this PV is equals to nRT, right? Means R is equals to PV by NT. So let us try to write the units. So what is pressure? Pressure is nothing but force per unit area multiplied by volume. Volume is going to be volume, right? Divided by moles, right? Unit of N is moles multiplied by temperature, which is going to be Kelvin, right? Which is going to be Kelvin, right? So unit of area is going to be, let's say, meter square in SI unit. Force is going to be, right? For let us keep force as it is. Volume is going to be meter cube. Moles is going to remain moles, and temperature is going to be Kelvin, right? And hence, when we write R, we get R is equals to force by length square multiplied by length cube, right? This is equal length square, right? This is length cube divided by moles into temperature, right? Moles into Kelvin, which corresponds to, which becomes, when we cancel this out, force into length divided by moles into Kelvin, right? But what is force into length? Force into length is nothing but work done, right? Hence, R is nothing but work divided by moles into Kelvin. Thus, what we can say is R represents work done per degree per mole, energy per degree per mole. So there are various values of R. So I'm going to draw the table for different values R. So clearly the value of R depends upon the units of this thing, right? So we can have one value of R in SI units, some other value of R in CGS unit, so on and so forth, right? Let us try to understand the value of R in units of V, which is volume, right? I'm going to the first column, then required P, then the value of R value, which we get. First is, then the unit is liter, and this is ATM, liter ATM, and this is going to be 1. First value of R. So for this, the value of R is going to be 0.0821 liter atmosphere Kelvin inverse mole inverse. Okay. Second is going to be when this is in milliliter and this is in atmosphere. This is going to 82.1 milliliter atmosphere Kelvin inverse mole inverse. Okay, it's going to be liter. However, pressure is going to be in bar. In that case, this is going to be 8314 liter bar Kelvin inverse mole inverse. Okay, and this is in decimeter cube is nothing but liter, right? So this is going to be bar, right? So in that case, this is going to be the same value, right? 0.08314 liter or decimeter cube dm cube bar Kelvin inverse mole inverse, right? The fifth one is going to be most important one when it is in SI units, right? When it is in Pascal. In that case, it is going to 8.314 Pascal meter cube Kelvin inverse mole inverse, or in other words, we can write it 8.314 Newton meter Kelvin inverse mole inverse, or 8.314 Joule Kelvin inverse mole inverse. Okay. So it may be noted that although R may be expressed in different units, but for pressure volume calculation, R must be taken in the same units as those for pressure and volume. Let us try to solve an example. So question number 1, at 25 degrees centigrade and 760 mm of Hg, a gas occupies 600 milliliter of volume, and we are asked is what will be its pressure at a height where temperature is 10 degrees centigrade and volume of the gas is 640 ml, right? So what we are given is P1 as 760 mmHg, we are given V1 as 600 ml, we are given T1 as 25 degrees centigrade, which is nothing but 298 Kelvin, right? Then P2 is unknown to us. V2 has been given as 640 ml and T2 has been given to us as 10 degrees centigrade, which is 283 Kelvin, right? So we just use we use the ideal gas equation, which is P1 V1 by T1 is nothing but P2 V2 by T2. When we rearrange it, we get P2 is equals to P1 V1 by T1 multiplied by T2 by V2. So we just plug in the values. P1 is 760 multiplied by V1 is 600 divided by 298 multiplied by 640 by 283, right? So when we solve this, we get P2 is equal to 676 mmHg. Okay, this is the answer. Let us understand one more thing about this ideal gas expression, density. So how this expression can be written in terms of density and molar volume. So density and molar mass of a gaseous substance. So we have that PV is equals to nRT, right? So what is N is going to be what? Mass divided by molar mass. We just substitute. This is going to be M by M multiplied by RT. So this is nothing but mass of gas, molar mass. Going to be nothing but RT, right? So we rearrange, we get P into M. P into M is nothing but M by V. What is this M by V? This is nothing but mass of gas by volume of gas. Let's say kg by meter cube. This is nothing but what? This is nothing but the density of the gas, right? P by M is nothing but rho RT, right? Where rho is the M by V is nothing but density of gas at TNP, right? Let's solve an example. So the density of a gas at 27 degrees centigrade and 1 bar pressure is 2.56 grams per liter. Okay, what we have to do is we have to calculate molar mass of the gas. So we are given temperature as 27 degrees centigrade, which is nothing but 300 Kelvin, and pressure as 1 bar and density has also been given to us as 2.56 gram per liter, which is going to be nothing but 2.56 gram per dm cube, right? And we know the expression Pm is equals to rho RT implies M is equals to rho RT by P. So rho is going to be 2.56. R is going to be, we are going to look at the table which we have seen previously. So R value comes out to be 0.083, right? Bar per bar decimeter cube by mole per Kelvin, right? Multiplied by temperature, which is 300 Kelvin, divided by 1 bar, right? So if you want to look at the units, so it's going to be gram per dm cube. I just write like this: gram Tm minus 3 multiplied by bar dm cube mole inverse Kelvin inverse multiplied by Kelvin divided by bar, right? Molar mass comes out to be 63.74 gram per mole, right? So the next which we are going to study about is Dalton's law of partial pressure, right? Dalton's law of partial pressure. So what does this law tells? This law tells that the total pressure exerted by a mixture of two or more non-reacting gases in a definite volume is equal to the sum of individual pressure with which each gas would exert if it occupies the same volume alone at constant temperature. So this law states that the total pressure exerted by mixture two or more non-reacting gases in a definite volume is equal to the sum of the individual pressure which each gas would exert if it occupies the same volume alone at a constant temperature. So we'll pick up from this statement in our next class. So we'll in a summary, what we have studied in this classes, we have studied about the remaining class laws which we have not covered, which are namely Avogadro's law, right? First is Gay-Lussac's law. Then we have studied about Avogadro's law. Then we have studied about the ideal gas equation. We have derived it using two methods, right? Derivation, and then we have solved some examples. And at the end, we have done just a brief introduction to Dalton's law of partial pressure. Okay. So in next class, what we are going to study, we are going to complete the Dalton's law of partial pressure, and then we are going to delve into the kinetic theory of gases, right? And then we are going to study the postulates of kinetic theory of gases and then its implications, and then we'll try to explain these laws based on the kinetic theory of gas, right? So I thank you all for attending this class, and I hope to see you all again in the next class. Thank you.